seeing structures,
we were surprised.
surface
We
characteristics.
expected this body to be rather like the moon.
Imagined.
This was quite an interesting discovery. It was one that we thought we might find.
Command Center for the Deep Space Mission, which in the past few days has carried the eyes of men farther than they've ever been.
And the science is pushed in amazing.
Just last
like
night,
fitting a jigsaw puzzle
we
together.
had these frames come back from 2 billion miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour.
Good morning, and welcome to the 5 o'clock edition of Voyager Update. I'm your host, Suzy Dodd. At 5 o'clock a.m. Pacific Daylight Time, Voyager is 510,000 kilometers, or 317,000 miles above the swirling cloud tops of Neptune, and it is speeding away from Neptune at a rate of 39,000, or 119 miles per hour. In the past few hours, you've seen some remarkable pictures of the Neptune's moon, Triton. We have a hard copy image here of Triton, and this shows the pictures that you've been seeing recently. They are from an observation called VT Map. VT Map maps the bright limb of the Triton, and it takes mosaics. In other words, we scientists scan from the outside images first, and then they come back and do the inside. So they go from the outside and down each side, and then back to the inside, with the last picture being the ones closest to the terminator, right in the middle, so they can have the best resolution on the body. We have a computer animation of this VT map observation that we would like to roll for you now. Okay, what the spacecraft is going to do here is it's turning toward VT map, taking a picture, and then nodding back toward the Earth. It's using a maneuver compensation to capture the pictures on Triton with the least amount of smear. And it lays down these footprints or narrow angle images in this mosaic type pattern, as I had previously shown you. Now, we also have some recent pictures of VT Map that we would like to call up. These were taken just a few hours ago, and they're really very exciting. In this one, you can see that there's some sort of ridge on the right-hand side and a lot of craters or just rough surface features on the left-hand side. In the next photo that we'll bring up, it seems to be a little bit smoother, and again there seems to be some kind of ridge in the middle that sort of divides it, the smooth side being on the right-hand side and the more rough surface on the left-hand side. And there's a third image, and this shows the limb of the planet, and again it seems to be a little bit smoother on the right-hand side. Up toward the top on the limb there is a dark crater, what appears to be a crater. I have to tell you now that I'm just guessing from my own point of view. This is not a scientific analysis by the imaging team. They will definitely be giving us some more information in future press conferences about these images. And the fourth one is another picture on the lower end of the limb. And again, you see a couple of dark spots on Triton's surface. Triton appears to be very interesting, and I'm sure that all the scientists here have been up all night, are very excited to see these pictures coming from what we call the VT map observation, being a map of the Triton surface. With us this morning, we have Dr. Jay Holberg. He is a member of the ultraviolet spectrometer team, which works here at JPL. Good morning, Jay.
Good morning.
Can you describe for us first what ultraviolet light is?
Certainly. Let's see, first of all, from the University of Arizona.
Okay. Thank you.
And ultraviolet light, the type that we're looking at, is very short wavelength light. The eye is sensitive to light around 5,000 angstroms. Angstrom is a very short measure of distance. The ultraviolet that we're looking at is about 4 times shorter than that. It's at about 1,200 angstroms.
So it's light you can't see with
It's light
your
you
human
can't see,
eye.
and it's light that never gets through the atmosphere.
Never gets through our own
that's right.
atmosphere. Okay.
You have to observe it from space.
Uh-huh.
And the instrument was designed primarily to look at emissions from the outer planets. This is hydrogen, helium emission, emission from hydrogen molecules, and this emission arises in the atmosphere of the outer planets, and that's what the instrument was designed to study, were those emissions.
Okay. Now, you've just recently completed a ring occultation observation
That's
with
right.
Voyager using the star Sigma Sagittarius.
That's right.
Can you tell us a little bit about how that went?
Well, it appeared to be successful. We certainly saw the signal from the star Sigma Sagittarius. What we do is we watch the ring pass in front of the star.
So that it's the stars out here and then the ring in the spacecraft.
That's right. And when the star passes behind the ring, we see a slight dip in the light level, and that would indicate then that we've crossed the ring. From that, we can deduce something about the amount of material in the ring. Now, of course, these rings have been observed by the same technique from the ground.
Okay.
With telescopes from the ground, the planet and the ring system pass in front of a star. People on the ground watching, you'll see the light dip, and that indicates the presence of the ring.
Okay. Do you have a
Yeah, I have some
pictures you'd like to show?
This is some data from last night. This is not very impressive.
that
It's
right
a
over
very,
there.
very small feature, if it turns out to be the ring at all. Can you see that?
Okay. We should.
Let's move this.
I'm going to start in the beginning. Is that upside down?
Let's see here. Yeah, it's upside down.
Okay.
Now we get this right. There we go. All right.
I can make that a little smaller here.
Okay.
That's easier.
That's fine.
Okay.
Make it too small, you won't see it. All right.
Small rings, huh?
This is time
Okay.
marching along here, and each one of these samples is the signal from our instrument every 3.2 seconds, every third of a second. And you can see the signal is very steady, indicating we're looking at free space. We're not seeing anything passing between us and the
and this
instrument.
top one.
That's
okay.
right. The suspected ring is right there, that small blip. Okay. The reason we suspected that is a small blip and not just a statistical fluctuation is that it occurs approximately at the right time and at approximately the right level to be the ring. Now we'll have to confirm this with other instruments, primarily the PPS, which is doing the same.
Which also did the same
The
star
very
occultation.
same occultation was doing
Great.
this simultaneously with us. And if they see it at the same
So
time
that,
we did, then
yeah,
it's a
that
good
very
indication.
small dip means then that it's a very, it's not very dense
It's
material
not very
for the
dense,
ring.
that's
It's
right.
just- do you have any
It's a
estimate?
few kilometers wide,
Okay.
and
That's-
it diminished the light by a few percent,
Okay.
5% perhaps.
So it's not dense. Does that mean the particle size then will be very small also?
Well, that
Can't.
it doesn't necessarily tell you anything about
Okay.
the particle size, unless you have other wavelengths at which to compare.
Okay. And this
Okay.
was done inbound.
This was done
To
last
Neptune.
night inbound. That's right, before we crossed the ring plane.
Okay. Now you also inbound had a planetary occultation using the same idea with this, using the sun as your
That's
star
right.
this time, and following it as it goes behind the planet Neptune.
That's right. We watch the sun set into the atmosphere of the planet, and when we do that, here we just sum all of our signal into one number. When we watch the sunset, we actually take a spectrum of the sun every third of a second as it passes into the atmosphere. And from that, we can watch the different levels in the spectrum change as the different gases are absorbing out different parts of the spectrum.
By different levels, you mean different wavelengths.
Different
Come
wavelengths,
back
that's
to
right.
The instrument.
That's right. We'll see hydrogen, we'll see hydrogen molecules, we'll see methane. And when this happens, by computing the rate at which the signal is absorbed, we can tell the height in the atmosphere, the concentration, and the temperature, and the makeup of the atmosphere.
Okay, now
this is a very upper atmosphere. This has nothing to do with the clouds that we're seeing down below.
I see.
This is very, very high in the atmosphere.
Okay, so all that data though was stored on the tape recorder.
That's
and you
on the
sort of
tape
have
recorder.
yet-
We won't know until
You don't
tonight.
know how well it turned out until tonight when it
Until
gets played
tomorrow when
back.
we get it back. That's right.
Yeah.
Mhm.
Okay. Now UBS has been obviously on the spacecraft for 12 years, like all the other instruments.
That's right.
But you are unique in a sense. You're the only imaging instrument that takes data during what engineers call their quiet cruise period, being that's the period between the planets where we
That's
don't
right.
have a planetary encounter. And I understand you also plan on doing that after you go by Neptune, the so-called star observations. Can you
That's right.
describe those a little bit?
Yeah. We hope after the encounter is complete to continue to observe stars with our instrument. These instruments are quite small. They're about the size of a shoebox.
The UVS.
The UVS, they're small spectrometers, but we have the luxury of very, very long integration times. We can stare at a star for a long time, build up a signal.
A long time being
Days,
weeks and
weeks if we
weeks,
need to.
if you can,
That's
yeah.
right. And the principal thing that we do is we observe at very, very short wavelengths. And this is where the hot stars are emitting most of their flux. If I could show maybe a stellar spectrum, you could see. This is, in fact, a spectrum of Sigma Sagittarius. This is the star that we went through the rings with.
Oh, okay.
All right.
Can you describe it a little?
Yeah, right. This is the band pass of the instrument. This goes from 500 angstroms to
So you
1700
have
angstroms.
wavelength on the bottom.
That's right. The light we would see on the ground is way over here somewhere,
So it's out
off
of
camera.
the picture, right?
All right.
Okay.
And this indicates that the flux is rising very rapidly towards shorter wavelengths. It's cut off right here at about 900 angstroms by
Okay.
hydrogen in the interstellar medium.
Okay. And this, you said the right-hand side is, or excuse me,
the
the
left-hand
axis there
side, right. This
is counts per second.
counts per second. That's right.
Okay.
This was.
So this shows like a burst.
No.
Or not a burst.
It's the spectrum of the star. It's the
I see. It's
distribution
of
of
wavelengths.
yeah.
Okay.
And what we were doing in that ring occultation was we were summing this entire spectrum and just reporting one number.
Okay.
Because usually the ring particles are absorbed, they're insensitive to the wavelength. You simply get a constant attenuation of the signal.
Yeah, and I understand that you can take, like you said earlier, your instrument is sensitive to wavelengths that we can't even see here from
That's right.
ground-based
That's right.
observations. So
There are satellites in Earth orbit that allow you to look in the ultraviolet, but they stop right here at about 1200 angstroms.
Okay.
And so right now we're the only instruments, this is Voyager 1 and Voyager 2.
Right.
We can actually look shortward of this
So you're
1200
really,
angstrom
yeah,
cutoff.
you're really getting unique data
That's
on
right.
these stars
That's
that
right.
no other instrument can
That's right,
create.
at the moment. That's true. And hopefully in the future, NASA, other agencies may launch satellites that can look in this region. But right now we're the only instruments. That's right.
Well, good. Thank you very much,
All
Jay.
right.
And we hope that your occultation data is good and that you get some exciting results in the next few days.
All right. Well, thank you very much.
We will continue to marvel as these images come back from Neptune and also Triton and also the other scientific data that comes back. I'm sure it's all very exciting for the scientists, and today will be a great day here at JPL. For now, this is Suzy Dodd, and this is Voyager Update.
0 and liftoff.
We're seeing structures, we're
Oh, we
seeing
were surprised.
surface
We
characteristics
expected
which
this body to be
really
rather
not
like the moon.
imagined.
This was quite an interesting discovery. It was one that we thought we might find.
Command center for the deep space mission, which in the past few days has carried the eyes of men farther than they've ever been.
And the science is pushed in amazing.
Just
It's
last
like
night,
fitting a jigsaw puzzle
we
together.
had these frames come back from 2 billion miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour.
Good morning, and welcome to the 6 a.m. edition of Voyager Update. I'm your host, Suzy Dodd. At 6 o'clock a.m. Pacific Daylight Time today, Voyager is 576,000 kilometers, or 356,000 miles, above the swirling cloud tops of Neptune and traveling away from that distant planet now. The spacecraft continues to send back fascinating data to scientists here at JPL. We've been seeing a lot of images recently, but we'd like to turn now to the plasma wave subsystem. And with me now is Bill Kurth, one of the investigators from Plasma Wave. Good morning, Bill.
Good morning.
Can you describe for us basically what plasma is? Because people, I think, get it confused with either electrons or atoms or, it's something like that, but they're not exactly sure what it is.
That's right. Well, basically what a plasma is, it's a very hot gas. It's so hot that the electrons have been stripped from the atoms. And instead of a neutral gas like we have here in the atmosphere of the Earth, you have an atmosphere that's composed of electrons and ions, charged particles.
Mm-hmm.
And in fact, what we're talking about is the environment around Neptune. We have a structure which we call a magnetopause. This is a bubble in a plasma. The overall plasma is called the solar wind. Now, what happens is the top of the atmosphere of the sun actually boils off the top of the sun, and it forms a wind, which we call the solar wind, that speeds out from the sun at a speed of 400 kilometers per second on average.
Wow.
And this blows past each of the planets, and in fact, it's a supersonic wind. And just as in the atmosphere, if you fly a jet aircraft in the atmosphere above the speed of sound,
Right.
you'll have a sonic boom.
Right.
And in fact, when the solar wind comes and sees this magnetic bubble of the planet as an obstacle, it creates a sonic boom around here. What we hope to study with the plasma wave instrument at Neptune is how the plasma out here in the solar wind interacts with the plasma inside the magnetosphere at Neptune. And so as we travel on this trajectory close to the pole and then down out this way,
Right.
we will see very strong interactions between the various components of the plasma, the electrons and the various ions.
Okay, so you're interested in how the solar wind plasma reacts with the plasma that's surrounding
That's right.
Neptune. Well, what can that tell us about Neptune if we're studying the plasma?
One of the basic energy sources at Neptune is the sun, and it's not just the light that shines on the surface of the planet, but it's this radiation, the solar wind that comes in. And it's important to understand how the energy in the solar wind finds its way into the interior of this magnetic bubble.
Okay, so the solar wind may affect the interior of Neptune and maybe the atmosphere too?
Yes,
I know you're not an atmospheres person, but
there's evidence, and it's fairly weak evidence, but evidence nevertheless that at the Earth, for example, activity at the sun, which causes variations in the solar wind, can in fact affect the weather on the Earth. And so there's very clearly a mechanism for the energy out here to find its way into the atmosphere of the planet. We simply don't understand that process very well.
okay, and so by studying some of these outer planets, we'll be able to get a comparison between and get a better theory on it. Also, I wanted you can discover things about the magnetic field from the plasma too. That's correct too?
The magnetic field and the plasma are intimately tied together. The plasma doesn't go very far without dragging the magnetic field with it, or vice versa. So I guess I'd like to talk a little bit about the instrument itself.
Okay.
And maybe the best way to do that is to show an example of data.
All right, let's call that up.
This actually is a example of data that we saw.
This is from Uranus.
From
right?
Uranus, the day of closest approach. And you can think of this as a voice print, if you will. What we've done here is we've plotted on this axis frequency going from 10 cycles per second, or 10 hertz, up to 56 kilohertz. And the audio frequency range is basically in the central portion of this band.
All right.
This axis is time, covering one complete day.
Okay.
And we use colors to indicate the intensity of waves. So if you see something red in this plot, it corresponds to a very intense wave. In this case, it's at a frequency of about 1 kilohertz, and it's late in the day. Now, the plasma wave receiver consists of two different sections. It's got two modes of operation. And this is the output of one of those modes. We basically have 16 discrete frequency channels covering this entire frequency range.
Okay.
And we operate it similar to the way a scanning police monitor works.
You go through all the channels.
That's right.
Sort of
you
one right after the other.
Let the thing sequentially go from one channel to the next, and at each channel it stops just long enough to monitor the intensity of waves at that frequency, and then it goes on to the next. Now, it's important to realize that what we're measuring is electric energy. We use the two dipole and the two whip antennas on the spacecraft, and they measure an electric field.
All right, we could show maybe where the PWS is on this model of the spacecraft.
Yes. It's these two long antennas. Each one is 10 meters long, and the receiver is tucked up under here on top of the spacecraft bus. And so if you have a disturbance in the plasma, it will create an electric field, which is received by these two antennas. Now, the fact that the energy that we're measuring is in the frequency range that the human ear can hear means that if we find a way of converting that energy to sound energy, we can actually listen to what these antennas are picking up.
I remember hearing sort of the sounds of Uranus. Are we going to have sounds of Neptune played here at one of these press conferences?
Yes, I'm sure that on the tape recorder on the spacecraft right now, there are many very interesting sounds.
That will be exciting.
And actually, that brings us to the second part of the second mode of the plasma wave receiver. Instead of having 16 discrete channels, we also have a wideband mode, which runs from about this frequency, 40 hertz, up to 12 kilohertz, and that is right in the middle of the audio frequency range. We get basically the waveform, the direct waveform of the signals that hit the antenna, and we record those on a tape, and we can play them back and then listen to the electric field signals.
You hear the eerie sounds of Neptune. Going back to this picture, what's happening out here where it's sort of early in the day, but there's some high intensity type marks? Can you describe what maybe we're seeing there? This is from Uranus, but we will see probably the same thing.
That's right. This is a good section of data to look at because first of all, we understand this. We've had a few years to look at this, and we think we know what's going on here.
Can't do science overnight.
And let me start out here in at closest approach and work outward.
Okay.
At this point in time, we did go closest to Uranus, and you see that the dominant thing that we see in the spectrum here is this band of emissions along here, and in fact, here they get so intense we're into the red here. These we call Whistler mode waves, and what's going on here is the plasma is causing a kind of a radio emission. It doesn't propagate away from the planet, though. The waves interact with the electrons and eventually cause these electrons to get kicked out of their orbit and come crashing down into the atmosphere. And we believe...
Screaming all along, or whistling,
screaming
as
all
I like
along,
to say.
right.
Yeah.
We believe these waves in particular may be responsible for generating the aurora that we're seeing on Uranus.
Auroras being like lightning?
The northern lights.
Northern lights.
Exactly. At higher frequencies, we see emissions that actually start in our frequency range and continue on above 60 kilohertz and into the planetary radio astronomy frequency range. These are radio emissions that are generated in the magnetosphere of Uranus and propagate freely away. Even a very distant spacecraft can
pick up the planet.
Right. Now, working back out, you notice there's a very thin line at this point in time. This represents a very broadband burst of electric field energy.
Yeah, all the frequencies probably.
That's right. This corresponds to the bow shock. I mentioned earlier that when the solar wind runs into this obstacle, it's very similar to a supersonic aircraft and a sonic boom. Well,
and you're hearing it here.
This is the plasma equivalent of the supersonic boom.
Yeah, it's like the shuttle came over L.A. I think it woke quite a few people up early in the morning, so that was a sonic boom, and that's what Voyager had just a little while ago as it went past Neptune.
And in fact, you see this band of emission preceding that. This band of emission we call electron plasma oscillations. This band is caused by electrons that are reflected and accelerated at the shock and go streaming back upstream.
They're coming from the solar wind. They hit the bow shock, the interference frame, and then they bounce back again.
That's right.
And that's what you see there.
When they stream back into the solar wind, they cause an instability, which results in these waves. So this is actually a sneak preview that we're getting close to the
foreshadowing of
magnetosphere.
that you're going to maybe see the bow shock.
Right. Now, if we can go to the Vanessa display.
We have another Vanessa display to show. Can we call that up? Here it is.
Yes. This is the data that we received on the spacecraft yesterday about noon. And there's some periodic things going on here that are related to the instrument, and I'd like to ignore for right now.
Okay.
But you see this band of emission that's along here. These are precursors to the bow shock. They're the electron plasma oscillations
like we saw in the
saw at Uranus. And this gave us a clue that fairly soon we were going to run into the bow shock. And indeed, here's that broadband burst of turbulence that's associated with the bow shock.
And you saw, what time did you see that yesterday?
This was about noon.
About noon Pacific Daylight Time. Right. Well, great. So what do we hope to find at Neptune? I mean, you told us we've seen the bow shock. Have we sort of seen anything else that you can describe? Or?
Well, last night, Don Gurnett was on the show about midnight, just as we passed through the ring plane, and he, in real time, watched us pass through the plane which contains the two rings. Our experience at Saturn and Uranus was that this is a place where we are very likely to find dust that's not dense enough to be seen as a ring, but it's just a generally dusty
fine
place.
Sort of dust layer.
And when the spacecraft goes moving through that region, the relative velocity between the dust grains and the spacecraft is so large, 15 miles per second, I believe, that the dust particles actually explode upon impacting the spacecraft. And that causes a signature that we can detect.
So you're also, besides radio waves, you're also sort of you're counting or sensing the particles as they hit you too.
That's right. Close to the ring plane, we become a particle detector for a very short period of time.
That's great. And the data was, I understand, was quite intense last night.
Yes, we were actually quite surprised at how intense the signature was, and it was distributed much further from where we thought the ring plane would be than we expected.
So there's dust particles sort of farther out away from the ring plane that we
That's what the initial look at the data would tell us, and we're anxious to get back and look in detail and see exactly what the data show.
Well, great. Thank you very much, Bill, and we hope that we can hear some more about that at the 10 o'clock press conference.
Great.
Well, that has been our 7 a.m. update, and we hope that you have enjoyed it. For now, I'm Suzy Dodd, and this is Voyager Update.
1, 0, and liftoff.
We're seeing structures, we're
Oh, we
seing
were surprised.
surface
We
characteristics.
expected this body to be rather like the moon.
This was quite an interesting discovery. It was one that we thought we might find.
Command Center for the Deep Space Mission, which in the past few days has carried the eyes of men farther than they've ever been.
And the science is pushed in amazing.
Just
It's
last
like
night,
fitting a jigsaw puzzle
we
together.
had these frames come back from 2 billion miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour.
Good morning, and welcome to the 7 o'clock a.m. edition of Voyager Update. I'm your host, Jancis Martin. At 7 o'clock a.m. Pacific Daylight Time today, Voyager is 635,000 kilometers or 394,000 miles above Neptune and speeding away from the planet at a speed of 38,806 miles per hour. Day is breaking here at JPL after a long, wonderful night. The last few hours have been absolutely thrilling. The Voyager Project, the Deep Space Network, and a very excited horde of scientists have been presenting us with an exquisite encounter. While the spacecraft has been obediently carrying out each of its commands and sending back each eagerly anticipated set of data, the Voyager flight team and science investigators have been literally jumping up and down and shouting with elation at the onset of each event, and then plunging immediately into serious head-scratching and vigorous discussion. We viewers have been able to participate most directly with the imaging activities, watching high-resolution pictures of Neptune, Triton, and rings appear at the same time as the imaging scientists are seeing them for the first time. And you've heard a lot of discussion from various imaging scientists about their investigations over the past few days. It has been traditionally much more difficult for the typical Voyager viewer to participate in the non-imaging investigations. This is for several reasons. One reason being that their data has never been as readily available, that is, accessible for processing and analysis. Another reason has been that the non-imaging data do not look like pictures, that is, objects our eyes can more readily understand, like rings, moons, and planets. Several years ago, two organizations at the Jet Propulsion Laboratory joined forces to bolster the accessibility and visibility of the non-imaging data. The resulting capability, Vanessa, has been the source of those colorful representations of data seen here on the Voyager updates and at the first press conference. You've heard us speak of Vanessa before, and here today to tell us more about it is Pat Liggett, the Vanessa Implementation Manager. Welcome, Pat.
Good morning, Jancis.
You're here to tell us about Vanessa, where it came from, what it's doing today.
What it is.
Yeah, what's it all about? People have heard about it, and I think at first wondered who this mysterious Vanessa was.
Well, what Vanessa starts out as is an acronym. Vanessa stands for the Voyager Neptune Encounter Science Support Activity. And as you mentioned, it was put together to support the non-image science people, or a lot of the fields and particles and waves people. And as you mentioned also, it's non-imaging, so we're doing line plots and spectrograms as opposed to the classic pictures that most people see.
Yeah. And where did this all get its start?
Well, it initially got started, the initial desire to do it happened at Uranus when one image was created, or one display was created for one of the experiments. The scientist who used that was so happy with what he had that the word got out, and it was decided, let's try this for Neptune Encounter. Let's get the people that get the fields and particles people their science data in real time. Let's give them some ability to display this data, and let's make this final encounter something that all the scientists can present their information as quickly as possible to the public, and to get access and be able to analyze their data as quickly as possible.
Well, what has it been like in the past when there wasn't this capability? When you say get it in real time, what sort of time frame were we talking about before?
Well, in the past, the science teams, the fields and particles people, the waves people, the non-image folks, got their data usually anywhere from a few hours to a few days after it was already on the ground, and certainly longer than what the image processing or the imaging science people got theirs. And what Vanessa does is it's able to give them data in real time and allow them to begin working on it right away.
I see something twinkling away over here. This is one of your displays here?
When we first developed Vanessa, as part of this initial plan, it was desired by the Voyager Project and by science teams to have basically 3 goals. The first was to get the data out in real time, and we have done that. The scientists have brought their equipment in from all over the country, and they connect up to the Vanessa system and get their data electronically in real time, as mentioned. The second thing that we were asked to do was create displays, create graphics. And so what we do, and what you see on this monitor here, we take that same data that scientists are getting, and we create our own graphs. This is a Vanessa-generated graph for the plasma wave experiment. And we're able to run real-time data through it, or as we see here, this is moving very quickly. What we're running through here is database data from yesterday. And we're catching up as we move along. This is, as you can see, it's August 24 down there. We're able to do this with our graphs, and we have graphs for each of the experiments, plus spectrograms.
Why do you have your own graphs in addition to what the scientists have developed?
Well, the reason we have that is, well, actually 2 reasons. One is for the people here at JPL. There are experiment reps that work here at JPL and support the scientists, and they needed something that they could use. The scientists have many of the scientists have their own equipment, and they brought their own graphics to do their own displays, but the local people here, the experiment reps, do not. Also, some of the scientists did not bring equipment to hook up to Vanessa. They brought equipment to hook up to the standard system that is part of the Voyager project, but they did not bring anything to use with Vanessa, and so we also have displays for them. They can sit down at a workstation that we have provided and run the same displays that we have. And finally, the scientists who have their own equipment and their own graphics displays look at theirs and look at ours, and they do some correlation, it's a comparison to make sure that what they're seeing on one display, they're seeing on another display. So they can compare the 2 and make sure everything is what they thought it would be.
Presumably then they have up to maybe 3 kinds of ways of representing their data, because they still have their old capability. Isn't that true? The way they have traditionally gotten their data in the past is still there.
Correct.
Right.
Correct.
And now they have new ways of looking at data.
That's right.
I think from what we've been seeing on the updates and hearing at press conferences that the science return seems to be a lot faster now from having this capability in place. And I know people have been casually mentioning, Vanessa this and Vanessa that, so it seems to be having a real impact here.
They seem to be using it a great deal. From what we've been hearing, they seem very satisfied with what they're seeing also.
What's it like over in the lab?
At times it's crazy. We had whenever we have anything interesting happen, when the scientists start seeing something that they consider to be a new discovery or new information that they were hoping to see, the place just fills up. We'll start out we have 2 rooms in use. We have a laboratory and then we have another room. We have 3 of the experiments with their equipment in one room. We have 2 experiments with their own equipment in another room. And then the 2 groups who did not bring equipment to hook up to Vanessa are also in our lab. And normally you'll see representatives from all those experiments in there, so you've got a fair number of folks to start with.
So how many is that? Is that 7?
Well, there's 7 experiments, so you can easily have 14 to 21 science people in there normally, plus a couple of operators of our own and some of our own support personnel. And when somebody starts seeing something that's interesting, they're beginning to witness something that they've been expecting to see, or it catches their attention. They say, well, there's something very interesting happening right here. All of a sudden, you wind up with people coming in from all over. All the scientists, all the science experiments that we support, they'll contact other representatives who are on the other system in another building, and they'll come over. So we'll have 40, 50 people in the room. So the place is just jammed with folks standing around and hovering over their terminals and watching what's going on and inputting new parameters to see if there's another way that they can look at their data and bring out the interesting information.
Well, another thing that I think goes a lot when you have these displays all together in one room, can you tell if there is more comparing of data between investigations as well, in addition to people comparing their plots against your plots? Are you also getting more than one investigation comparing data?
We see a lot of folks walking around and chatting with one another. We'll notice that the plasma science people and the LECP people are on a long table. The LECP is at one end, PLS is at another end, and we'll see them talking to each other. Well, what do you see, and how does it look to you? And for instance, whenever magnetometer begins seeing something that might be of interest, and they see something that might be starting a situation that the scientists have been looking for, they're sort of the precursor. So they say, well, we see this, and then everybody's going rushing to their terminals. Well, I see something, but I'm not sure it's the same thing. And so they all rush back and they all sit down with the MAG folks and watch what they're doing. They'll go over from MAG folks over to the plasma wave folks over to the plasma science. And so you'll just see this little crowd moving around the room looking at each other's display.
That seems like a good move. I mean,
It is.
You hear about that more and more in the science arena, making data more readily available, more readily visible, more readily interpretable by the casual user and by the science users. So it seems like this is a real good step in the right direction. Do you have some displays to share with us today?
Yes, the other thing that we do, the third goal that we have, was to provide information to the Public Information Office or over here to the TV studio. And we do that by, we have a scan converter hooked up to a computer, and on that we basically take computer displays and put them into television video so people can see them. And that's what you see. I believe this works like this, no? Yep.
Yeah, you hold it
okay,
down.
you see this system here where we have these displays going. We have this type of display. This is one of ours, a Vanessa display that we created. We're also able to present the displays off the scientist's computer and send that over here. For instance, John Louis sitting at a terminal behind us can ask for a display on channel A, which is a back station that's run by the plasma wave folks. Now their display, this is their graphic. They created this themselves. They brought it on their equipment. This is their machine. And we have cables running over their machine. We can switch to them by just pressing a button and bring their display up so that Bill Kurth, who was here earlier at 6 o'clock, he could just say, well, I'd like to see this display, or I'd like to see this other display, and they just press a button, flip it over, and they bring up his display.
So some of those displays are generated here, and some of them are coming from back in the lab?
We can do it any way anybody wants it. We can generate them over here, we can generate them over there. The operator over here can bring up a display over there. He can bring up a display over here. He can switch, he can request that an operator at the other building switch over to this other channel. For instance, we have yet a third one, which is on a Mac over there, a Macintosh that the low energy charged particle
That's
people
something
have.
they can bring up
They
as
can
well?
bring that up also. So they can flip between, there's 3 different channels they can flip between. We can cable up to anybody in the room. We can bring
My
up any
goodness.
display they want. So the trick is that the scientists can come over here and say, well, here's my display, here's a Vanessa display, and they can jump between them and show either what's going on now, or they can show what went on before by, at Uranus and at
I noticed this is a Uranus display
right.
here.
they can do just anything they want to. All they do is just tell us, well, this is what I want to show over there, and we can just set them up and just by the magic of television bring up different displays from the different systems, and they can come over here and explain what's going on to people.
Have people brought their Uranus data with them to
Several of them
look
have.
at it while they're sitting over there
In fact,
too?
Plasma Wave brought not only Uranus, I think they brought Jupiter too. So they brought a bunch of them, and they were bringing up the spectrograms. If we can flip back to channel A again, the spectrograms are images created from non-image data. I mean, they look like a picture of some sort. And basically what PWS did is, I've seen them bring up, I think this is Neptune. I'm not even positive.
That's Neptune.
Yeah, that's Neptune. You have to check I have to check the dates on it to be sure, because they can bring up Neptune, they can bring up Uranus, and they can bring up Jupiter. And what I've seen them do is they'll flip between them to see how they look similar, how they look different. So it's kind of fun watching this, and with this particular system, then they can do it over there and then show it to folks over here, and the people here in the TV studio can turn around and feed it out to the world.
Yeah. So do you think they're getting any sleep over there, or are they mostly hunched over their hot terminals?
That's pretty much it. I've heard that every now and then we'll get a little lull where there's just a few people in there, and then they'll all come back in, and it's around the clock. They're in and out all the time.
Well, I think that's really exciting.
It's been a lot of fun watching them, because they just, as you mentioned earlier, they get real excited. They see something they consider interesting. They're all jumping up and down and shaking hands. I mean, it's like somebody just had a kid. It's kind of amazing.
Well, thanks for coming
thanks
share
for
this
having
with
me
us
over.
today, Pat. Our next update will be at 12 o'clock noon Pacific Daylight Time. For Voyager Update, I'm Jancis Martin.